Hi there, my name is Matteo Cataneo and I'm a postdoc at the University of Edinburgh. In this talk, I'd like to share with you some of the exciting results of the work I've been doing in the past couple of years with a fantastic group of collaborators, where the overarching idea of this entire research program is to find a satisfactory solution to the modeling of the clustering of matter on cosmological distances, all the way down to the scales of clusters and groups of galaxies. And do this not just for ΛCDM, but for many possible scenarios beyond the standard picture. At the same time, though, we would like to keep the computational time for the theoretical predictions within limits acceptable for likelihood analysis, for example. Um, Obviously, 20 minutes is not enough time for me to delve into the details of my work and of my solution to this challenging problem. So if you're interested in the more technical aspect of this talk, of this work, of this approach, go check this series of papers on arXiv. All right, let's start. So you probably don't need to see me for the rest of the talk. Okay, good. So one would ask as a first question, why bother modeling all this complex and intricate phenomenology on small scales in the first place? Why just not restrict to these easy linear scales that we understand very well? Well, the answer lies in the exquisite quality of the data that will be produced by massive all-sky galaxy surveys coming online in the next few years, like Euclid and LSST. For example, the top panel of this figure shows that when we include more and more nonlinear modes, the convergence power spectrum experiences a tenfold increase in signal-to-noise ratio. In the context of ΛCDM, this allows to break degeneracies, and by doing so, we can, in fact, constrain the cosmological parameters from observations of the large-scale structure alone at the level comparable with CMB experiments. I'd say that even more important, though, is that by getting access to the nonlinear regime makes it possible to detect signs of new physics that would be otherwise hidden in noise. And that's the case for the modified gravity model represented by the magenta line in the lower panel. To discriminate this model from standard gravity, we must get access to the information locked in the nonlinear regime. Otherwise, we wouldn't be able to discriminate from standard gravity. However, if we are to capitalize on this high quality data, we will need equally high quality predictions. Now, we can think of the quality of these predictions as living in a three-dimensional space with speed, accuracy, and flexibility along the axis. And we want any method producing such predictions to sit in a place with a high score for each of these features. And why is that? Well, the prediction must be fast for parameter inference. Think of the hundreds of thousands of evaluations we need to reach convergence. And second, to avoid biased conclusions, we clearly want them to be accurate. And since we are searching for possible signs of new physics, ideally we would like an approach general enough to be able to produce predictions for a variety of ΛCDM extensions. Up to now, no method could do this, and that's also the case for perturbation theory, halo model, and emulators when taken individually. However, there is a way to combine these existing strategies in a framework that features all three of these properties: speed, accuracy, and flexibility, and requires no direct fitting to the nonlinear power spectrum from simulations. And I named this intersection the Halo Model Reaction Framework. So, what are the ingredients going into this framework? First and foremost, I have to introduce a new concept at the core of the reaction method, the pseudo or fake cosmology. The idea behind the pseudo cosmology is very simple. It's a universe where the linear structure grows like ΛCDM, but the difference really is in the initial conditions. So for any specific redshift, the initial conditions are designed to produce a linear power spectrum identical to that of the non-standard cosmology we want to have prediction for, which to differentiate from the pseudo-cosmology I just called the real cosmology. If you're confused, hopefully this cartoon will help you understand better. For simplicity, let's consider a beyond ΛCDM cosmology that changes the linear growth rate in the same way for all scales considered, which in practice, it means that the linear power spectrum is identical to that of ΛCDM except for its overall amplitude. A smooth dark energy cosmology would fit this description, for example, and for the purpose of this cartoon, it's our real cosmology. Now, we want the real power spectrum of the corresponding pseudo cosmology to match that of the evolving dark energy cosmology at, say, right at 0. Now, how do we set up the real and pseudo initial conditions? We just evolve back in time the smooth dark energy linear power spectrum using the ΛCDM growth function for the pseudo cosmology, and for the actual dark energy, for the real cosmology, we apply the actual dark energy growth function. So deep in the matter-dominated era, we would end up with a situation similar to this one shown here in this on this slide. By moving forward in time, linear clustering proceeds at different rates for the two cosmologies, until finally at Reggie 0, the two linear power spectra are exactly matched by construction. The second ingredient of the halo model reaction framework is, of course, the reaction, which is defined as the ratio of the real nonlinear power spectrum to that of the pseudo-cosmology. Now, using the halo model formalism, we can decompose the nonlinear power spectrum in two contributions. The first one is a one halo term accounting for intercluster correlations, and the second one is the two halo term describing correlations between different halos. In the reaction framework, we actually approximate the two halo terms with the linear power spectrum alone, and apply an empirical correction factor fully determined by standard perturbation theory and the halo mass function, as I'll explain in a minute. But first, let's have a look at some key properties of the halo model reaction. And for a moment, let's forget about the correction factor. On large linear scales, we see that the reaction converges to unity, and this is visible as the red curve in this cartoon. And this is exactly what we want from the definition of pseudo-cosmology. Because the linear power spectrum is subdominant on small scales, the reaction there reduces to the ratio of only one halo terms. So accurate halo mass function and mean halo properties are very important to predict accurate reactions in the highly nonlinear regime. Now, coming back to the correction factor, its purpose is to absorb all the phenomenology that makes the reaction to deviate slightly from unity on quasi-linear scales. So screening mechanisms in modified gravity belong to this kind of phenomenology, for example. And its particular functional form is somewhat arbitrary, but whatever function you decide to use, it must preserve the reaction properties I mentioned before as much as possible. So the functional form I picked seemed to work particularly well for all cases we looked at, and its two parameter, big E and K star, can be derived from our knowledge of the halo mass function and perturbation theory alone, so they are not free parameters. Last, we need to go from the reaction to the real nonlinear power spectrum. For now, let's assume that we can compute the pseudo nonlinear power spectrum to arbitrary precision with some other method, and I'll tell you in a few slides one possible strategy to do this computation. Then getting to the real nonlinear power spectrum is just a matter of multiplying the pseudo power spectrum by the halo model reaction. As simple as that. We tested this approach in some popular ΛCDM extensions, and here there are 3 examples within the broad class of modified gravity and dark energy cosmologies. But first, let me say a few words about effective gravity and DGP. So these two models are very different modifications to general relativity. The linear growth structure in effective gravity is both scale and time dependent. On the other hand, in DGP, linear modifications are only time dependent. And we can see that these differences result in the markedly different shapes of the dashed gray lines in the left and middle panels that correspond to linear theory predictions. But differences do not stop there. The suppression of the modifications in the nonlinear regime is also rooted on different physics. So in f over gravity, screening is activated by deep gravitational potential wells, in DGP by high density regions. So very different models indeed. Despite all this, you can see that the halo model reactions work well down to scales of about 1 H inverse megaparsec. And in both cases, as baseline, I use the pseudo nonlinear power spectrum of dedicated n-body simulations. The purpose of the right panel, instead, is to illustrate where emulators can enter the picture. So here, the pseudo nonlinear power spectrum is calculated with the Coyote universe emulator, and then I rescaled it using the halo model reaction. So again, accuracies reach percent level all the way down to small scales, also in this case. We are not restricted to modified gravity and dark energy cosmology though, and in fact, we can even add other matter species, for example, massive neutrinos. And here in this figure, I show that the computation of the reactions, just by assuming that neutrinos cluster linearly, can produce results, predictions that are in remarkable agreement with simulations all the way down to highly nonlinear scales for various neutrino masses. So far, I've assumed that the pseudo nonlinear power spectrum was given by some other method. In the text examples, I use the output of n-body simulations, but obviously we cannot run costly simulations for our likelihood analysis. That would take forever. And even worse, we can't run simulations for all ΛCDM extensions. That's unthinkable. But all is not lost. In fact, the emulator can come to the rescue if properly trained. As a reminder, I put up here the definition of pseudo-cosmology. And the most important bit of these definitions that we want to remember is that the pseudo-cosmology is nothing but a weird ΛCDM cosmology. Now, if a ΛCDM extension doesn't add any new physical scale, the 5 standard cosmological parameters are enough to define the shape and normalization of the linear power spectrum of the pseudo-cosmology, which means we can use the emulators already out there on the market to get the pseudo nonlinear power spectrum. For example, we could use Cosmic Emulator or the Euclid Emulator. And that's exactly what I did for the Evolving Dark Energy Cosmology test a couple of slides back. In general, though, ΛCDM extensions do introduce new scales. For example, think of the free streaming scale in massive neutrino cosmology, or of the Compton scale in f over gravity, or both when we add massive neutrinos to scale-dependent modified gravity. And the figure shows precisely what happens for these cases. The linear power spectrum ratio of the ΛCDM extension to that of ΛCDM itself is not just a constant. In fact, it has some characteristic shape that depends on the non-standard parameters. If we can find a way to include the information coming from these shape changes into a regular ΛCDM emulator, then we would be able to generate pseudo nonlinear power spectra. However, as I said earlier, ΛCDM can be extended in many different ways, and we can't possibly train the emulator on this endless list of scenarios. So we must be a bit inventive here, a bit clever, and come up with a strategy to include the shape changes in a model-independent way, or at least as model-independent as possible. One such strategy uses the tool of principal component analysis to reconstruct the pseudo over ΛCDM shape ratio. In practice, the shape reconstruction consists of 3 steps. First, we generate random shapes having some properties. And for the sort of test cosmologies we consider, like f over gravity, massive neutrinos, and their combinations, we want smooth shapes converging to 1 above a certain scale. This last requirement can be relaxed to some degree, but at this stage I'm just presenting a proof of concept emulator that can be further developed in the future. So to generate these random shapes, we use two independent algorithms, one based on Gaussian processes and the other on trajectory evolution. So some example curves are shown in the top panel of this figure that you see on the slide. The second panel from the top shows the f of r, massive neutrinos, and combined models of the previous slide overlap to all the 2,000 random shapes generated by the two algorithms. As a second step, we extract the principal components of the 2,000 random shapes. The first 8 of these components are visible in the lower middle panel. The final step in the reconstruction takes the actual shape of the pseudo cosmology and projects it onto the principal components. From the bottom panel, we see that by rewriting the shapes as a weighted sum of the first 8 principal components, the resulting curves match the input shapes to within 1% or even better. So at the end of the day, this procedure replaces the non-standard parameters with a set of weights, which is exactly what we wanted. So this way we can map a diverse range of pseudo-cosmologies to just a bunch of model-independent numbers, the delta alphas on the slide. Now, following what's pretty much standard practice these days, we trained a Gaussian process emulator on a Latin hypercube with training nodes living in a 13-dimensional space, where 5 dimensions are allocated for the standard cosmological parameters and the remaining 8 dimensions for the principal component weights. Again, since this is a proof of concept, we didn't actually run n-body simulations to generate the training set. Instead, we went for some surrogate alternative, and in our case, we used HaloFit. So what we want to test is the ability of the emulator to reproduce the output from HaloFit given the same input power spectrum and cosmological parameters. Turns out that 500 training nodes are enough to reach an accuracy of a few percent for viable ΛCDM extensions, as illustrated by the magenta bands in the left figure. We were also curious to see how the emulator performed for a non-standard cosmology we didn't even consider before. For example, one with an additional relativistic degree of freedom. And although this modification is very extreme given Planck constraints, the emulator works very well for this case too, as you can see from the results on the right figure. All right, so far I've talked about the accuracy and the flexibility of the reaction framework. How about its computational efficiency? Recently, we have released the React C++ library together with a Python wrapper, which we call PyReact. And this wrapper is especially useful for integration in cosmological parameter estimation codes like Cosmologies. This version of React can generate a reaction in 0.3 seconds, which is, I think, good enough for likelihood analysis. Keep in mind, though, that this computing time is not set in stone, and with further optimization, it can easily go down to 1/10 of a second. The code is organized in well-defined modules, so it's very easy to add models or to modify in general. At the moment, we have 3 model implementations ready for use. So we have Husavitsky f over gravity, NDGP, and the evolving dark energy. And in our next release, planned before the end of this year, we'll be adding massive neutrinos as well. So if you're curious and want to have fun with it, just download React following the link at this GitHub repository. So hopefully I convinced you that the reaction framework does tick all the boxes. With React, it only takes a fraction of a second to compute the Halo model reaction. In its current form, it's also 1% accurate for wave numbers up to 1-ish H-inverse megaparsec for all tested cosmologies, and even better than that for massive neutrinos. And it can be applied to a broad class of ΛCDM extensions. Through the Halo model, this method provides a strong connection between the Halo properties, such as their abundance and profiles, and the nonlinear clustering of matter. This can be very useful, for example, in cosmological analysis, combining cosmic shear and cluster data. What does the future hold for the reaction framework? Well, the modeling accuracy of the reaction itself in the highly nonlinear regime and the accuracy of the pseudo emulator can and will be improved. And for the emulator in particular, we'll replace HaloFit with proper n-body simulations. Also, thanks to the HILA model, the framework can easily accommodate the effect of baryonic feedback on the matter power spectrum. So we plan to include those as well in the future. It will also be interesting to look at other statistics like halo clustering in real and redshift space, and efforts are currently underway to extend the reaction to a more general class of scalar tensor theories and to include a self-consistent string on modified gravity and massive neutrinos. Hope you enjoyed my talk. Thanks for watching, and I look forward to the asynchronous and live discussions.